currently we've just talked about, so far we've talked about communicators only as being, I have to cut out the noise here, only as being just a bunch of processes. So we've only actually used ComWorld, but we're saying, you know, communicator is a bunch of processes, and we may in our mind think of them as being in a structure. So for example, in the traffic model or the message round the ring example, you imagined that they were in a ring. You know, the process I was was the neighbor of I plus one, and that it was a circular ring. But we didn't tell MPI that was just us deciding to do a number, or to call the neighbor I plus one, I minus one with cyclic boundary conditions. Now, actually, when you use communicators, you can actually tell MPI that information. You can say to MPI, look, I started off with MPI ComWorld, and I think of MPI ComWorld as just a bag of processes. There's no structure to them other than that their unique number. You can tell MPI, look, these processes are actually arranged in, and we'll talk about in this lecture, regular grids. So, and that is a number of usefulnesses. It can help in calculating who your neighbors are. Now, that's fairly trivial in 1D, I plus one, I minus one. But in multiple dimensions, you know, it can be a bit of work to map a 3D. If you've got a 3D problem and you want to split it up into a 3D grid, you've got to map the linear rank 0 to n minus 1 into some structure. And MPI allows you to do that within MPI with standard functionality. And also it can in principle be possible that MPI, once it knows that your processes are in some structure, that it can take advantage of that in terms of optimizing various communications, but we'll come to that later on. So virtual topologies give you a convenient process naming. We can start to talk about processes as being the process at position 3,1 at coordinate 754 rather than rank number 53. A naming scheme to fit the communication pattern, i.e. you can talk about the coordinates, and we'll see that it also allows you to compute neighbors. It potentially simplifies the writing of code. The example which I have associated with this exercise is to do with the message ring, and actually in one dimension computing your neighbors as I plus one, I minus one is fairly trivial. So in that particular case it isn't actually any more, it is probably more effort than it's worth, but it illustrates how you use these functions. And in higher dimensions, 2- and 3-dimensional problems, which are much more common in scientific and technical applications, that is the right thing to do. And I said in principle it can allow MPI to optimize communications, and I'll come back to that. Now, I did at one point consider dropping these lectures from the introductory course because topologies are something which not everyone uses, and I did and ah, but in the latest release, well, it's not like the third version of that book which I mentioned on the first day, Grop, Skellium and Lusk's book on MPI. It may have been in the previous editions, but I hadn't noticed it before. They have a list of some of the things which they were proud of in MPI and that they felt were fundamental design features and improvements on other message passing systems. And one of the things they quoted was virtual topology. So I thought, well, actually, we should keep it in there, and it is useful to know about. And also it allows us now actually to create our own communicators, which you wouldn't have done before. So that's quite interesting. So what you do when you create a virtual topology is you produce a new communicator. You say, here's a communicator, say MPI ComWorld, where the processes have no structure. And then you say, I want them to be arranged, and we'll talk about here as a 3D grid. Okay. Having done that, you get a new communicator, which in this case contains the same processes as the old communicator, but they now have a structure. And you can then use MPI's mapping functions to say, who is my process up, down, left, right, for example, my neighbor up, down, left, right. Now, that is a meaningless question in MPI ComWorld. They're numbered 0 to n minus 1. There is no sense of any interconnectivity between them. Once you create a virtual topology, you're telling MPI, look, they are connected in this virtual grid. And then you have mapping functions to compute the process ranks based on the topology naming scheme. So why might you want to do this? Well, I think the best example I can think of was the traffic model with multiple lanes. So what we did in the normal traffic model is we had a one lane and we split it up amongst processes in a 1D decomposition. And that led to a communications pattern which is identical to the message around a ring, because each process needs to speak to its neighbor at the boundaries, and we have these periodic boundary conditions. But actually, imagine you had multiple lanes. Here I've got a 4-lane road, or it's actually a 4-lane roundabout actually. You might want to parallelize in that dimension as well. You might want to actually split it up into a 2D grid, so that not only is it split up in that dimension, but you use 4. So if you had 6 processes, about 32 processes, you might split into so that the lanes were given 1 to each of 4 processes. So then you have 8, and the remaining 8 is, each lane is then split amongst another 8 processes, giving you a 4x8 grid. 1, 2, 3, 4, 5, 6. Yeah, 4x8 grid of processes. And so that's something you might want to do. But interestingly, it's not enough to just say, I want a 4x8 grid of processes, because if we remember the traffic model, if I was to evolve this traffic model, okay, then we would all move. But actually, the cars at the end reappear back at the side again, okay? So let's look at that again. The cars move, but actually, because we have periodic boundary conditions, we're thinking about a roundabout here, the cars reappear over here. So the neighbor of this process is that process around there, and the neighbor of that process down the way is that process there. However, that is not true in the other dimension, okay? The neighbor of this process is that process, but the neighbor of this process is, there is no neighbor, because this is a hard boundary. This is the edge of the road. It doesn't make sense. There is no process up. It doesn't make sense to say the neighbor of that process is this process. That's meaningless. There is no neighbor up there. So not only if you have what we're going to call a Cartesian topology, a grid of processes, do you have to specify the dimensions, you also have to say for each dimension, what are the boundary conditions? Are they periodic, cyclic, or are they non-periodic? And you can see in this example that the boundaries, that the horizontal dimension here has periodic boundaries, but the vertical dimension has non-periodic boundaries. And so you could call that a cylinder. If we had 12 processes in this 3x4 grid, this is an example, we could say that it's non-periodic in that dimension, okay, but it's periodic in this dimension. And we call that a cylinder because it looks like a cylinder. It wraps around in one dimension and not in the other. So, you know, if you're on a cylinder, if you go round and round, you come, if you're an ant running around a cylinder, you keep coming back on yourself, but that way you stop at the top. So that's what we're going to do. We're going to tell MPI, in this case, our 12 processes arranged in a 3x4 grid. And once you've done that, you can start referring to the processes by coordinates. You can say, well, this process, it may be process 5, but actually it's more useful to think of it as being process at position 1, 1 and 1, 2. And if you notice, you'll see here that the MPI uses a C-like naming scheme for its process dimensions. In other words, process 1 is at position 0, 1, okay? If you're a Fortran programmer, you think of element 1 being at 1, 0, because if you're thinking about Fortran arrays, in Fortran the first index is the fastest moving. In C, it's the second index. It's just a convention. So, but again, because MPI was written by C programmers, Fortran programmers just have to live with that, unfortunately. But it does allow us to say two things. A, rather than thinking of this as being rank 6, it's at rank grid coordinates 1, 2. And secondly, its neighbors are 0, 2, 1, 1, 1, 3, and 2, 2. Okay, and that's easier to think about than this neighbor of 6 being 2, 5, 7, and 10. So thinking, once you've imposed this regular grid-like structure on your processes, it makes sense to think of them as being labeling them by coordinates. And not only that, if you to ask who is the neighbor of this process in the second dimension, 1, 3, 1, 4 wraps around to 1, 0, and the neighbor down of 1, 0 wraps around to 1, 3. But in this dimension, the neighbor this way of 2, 3 is not 3, 3, but there is no neighbor, okay? So we want to be able to encode that into MPI. And hopefully the example of the traffic model kind of motivated that. So there are two kinds of topologies. There are things called graph topologies, which are general graphs. We're not going to cover them here because, well, until recently they weren't actually that useful, but that may have changed recently. But a graph topology is a completely unstructured grid. So the important point about a Cartesian topology, a regular grid, is that each process is connected to 4 neighbors in a grid. Okay, every process in 2D has 4 neighbors, in 3D has 6 neighbors, and 4D has 8 neighbors. Whereas an unstructured mesh is completely, you know, it's a, I should draw one here, but it's a completely random connection. It's a graph, and every process has an arbitrary number of neighbors, and you just have to list them. So it's not so convenient. It's a bit more verbose, and it's actually hard to come up with practically an example for this course. So I don't really cover them here, but they do exist. So if you're an engineer doing unstructured grid calculations, finite element calculations, and you say, well, actually, I have a very complicated mesh, finite element mesh, and when I decompose it, I don't get this grid structure, I get an equally complicated graph structure for the connectivity. You can encode that to MPI using a graph topology, and there are different inquiry functions there. But the simplest one to illustrate the concepts is the Cartesian topology. So in a Cartesian topology, each process is connected to its neighbors in a virtual grid. Boundaries can be cyclic, i.e. periodic, or not. And you can allow MPI to optionally reorder the ranks to allow it to optimize for underlying network interconnectivity. So we'll come back to that. That's a bit of a subtlety. And most MPI implementations don't take advantage of it, but it's useful to mention. And processes are identified by Cartesian coordinates. That's the most natural thing to do. So how do you create a Cartesian topology? Well, it's quite simple. It's MPI cart create. Let's create a Cartesian topology. You give an old communicator. You say how many dimensions there are. In our previous example, it would have been 2. You give it the dimensions of a little array, which in the previous case would have been, let's have a look what it is. The way I've drawn it here is 2, 3. Okay, so that would be the dimensions would be 2, 3. The periodicity would be false, true, or 0, 1. So the first dimension is non-periodic, but the second dimension is periodic, the way I've drawn it there. Reorder, now, if reorder is false, then it's guaranteed that the rank in the new communicator is the same as the rank in the old communicator, which is nice. However, if you say reorder equals true, you're allowing MPI to 2 by 3 or 3 by 4. Did I say 2 by 3? I meant 3 by 4. Sorry, I meant 3 by 4. So yeah, you specify the size. Okay, so you know, indexing arrays from 0 is stupid. You know, well, it may be convenient in programming, but you know, in maths we index arrays from 1 and matrices. So that is a 3 by 4 grid, and the indices go from 0 to 2 and 0 to 3, but it's 3 by 4. Does that answer the question? Yeah. So it is. I may have said the wrong thing there. It is actually. I'm in the wrong chat window. Sorry. Yeah. So I specify dims as 3, 4. I hope I said that correctly. Now, if you say reorder equals true, MPI is allowed to give a new rank to the process in the new communicator. And the reason it might do that is once you've said that the processes are in a Cartesian topology, okay, then MPI knows that you're going to be communicating in a grid, and therefore it knows who's going to be communicating with whom. So for example, okay, in this example, it would know that you're going to be communicating with your neighbors in that direction and in that direction. And we haven't talked about the mapping of processes to physical processors, but when you launch an MPI job on a real parallel machine, which is a cluster, a large supercomputer like Archer or Archer 2 is actually a cluster of separate shared memory nodes. So Archer is about 5,000 24-core nodes. Okay. It might be that if you're going to do a lot of communications in this dimension, okay, you want this process to be on the same node as that process, because it means that the communications between them is just in shared memory. But it might be with the default mapping of processes to processors, the communications along here are going between nodes, okay? And in that case, MPI might say, well, actually, if I renumber things, I can make sure that the communication is optimal, that more communication is happening on a node than off a node. Now, in practice, most MPI implementations don't take advantage of that, or the ones that do a bad job. But it's there. You need to be aware of it. It's simplest to specify reorder equals true, false, real, so that your rank in the new communicator is the same as the rank in the old communicator, i.e., your ranking, typically your ranking com world. But you can allow reordering. It's maybe worth, and if you do allow reordering, you have to recompute your new rank in the new communicator. So it's there in principle to allow MPI to say, given this communication structure and given the current mapping of processes to physical processors, that's going to lead to too much inefficient communications. I can do a renumbering and it can be better. But in practice, it's not often utilized. So you might say, okay, I have to specify the dimensions here. That's fairly easy here, okay? 12 processes in 2 dimensions, a 3x4 grid. What if I said to you, I have 1,280 processes and I want them in a 4-dimensional grid? It's going to be quite hard to do that. So you have to do a lot of factoring. So MPI provides you with a helper function called MPI dims create. You tell it how many processes you have, number of nodes, how many dimensions you want, and it gives you back a suggestion for how you should arrange them. It's just a suggestion. When you do MPI can't create, you say, I want these processes to be in this arrangement, okay? But the natural thing to do, you can compute that yourself if you want, but it's often easier to call MPI dims create. And MPI dims create will give you a suggestion, which for large numbers of processes saves you lots of sort of hairy maths and such like. So the core will try to set dimensions as close to each other as possible. Now, on entry, the value of dims is significant. So you create this array. If on entry the value is 0, MPI takes it as a sign that you are free for that dimension to be varied. Okay. However, if it's a positive value, non-zero value, then MPI takes that as as a constraint. So, for example, in this example, you might say, well, I want there to be 4 processes in this dimension because there are 4 lanes. Okay, so that's what I need. I need 4. Okay, this one I don't care about, but this one it has to be 4. So you can see there are situations where you might actually, require certain constraints. So remember, 0 means, so if you call MPI dims create, you say I've got 6 processes. I want a 2-dimensional distribution. And on dims, excuse me, before you call it dims is initialized to 0, 0, MPI has complete freedom. It might give you 3, 2, or 2, 3, for example. If you say I have 7 processes and I want a 2-dimensional decomposition, and I don't care what it is, there's only 2 answers, 7 being prime, 1, 7, and 7, 1. If you say I've got 6 processes, I want a 3-dimensional decomposition, and you say dims is 0, 3, 0, you're saying I want a 3-dimensional decomposition, and the middle dimension has to be 3. There's only 2 possibilities there, 2, 3, 1, or 1, 3, 2. Of course, you can give erroneous things. You can say I've got 7 processes, I need a 3-dimensional decomposition, and the middle dimension has to be 3. That doesn't work. It's erroneous, and you'll crash. So, well, it'll actually crash, actually. So non-zero values in dims sets the number of processes required in that direction. So make sure dims is set to 0 before the call. So that's an unusual, just an unusual thing. So that's typically what you do. You call MPI dims create. You specify what your number of dimensions is, any constraints. You get back a dims array, and then you pass that to MPI cart create, and it will give you back a Cartesian topology with the correct dimensions, or with those selected dimensions. Okay, so having done that, you now have your processes arranged in a topology, and you can start talking about mapping grids to ranks. So for example, MPI cart rank, okay, takes coordinates and gives you a rank. So you can say, what is the rank of the process at position 2, 3? And it will say its rank, whatever. So you give it a little array of coordinates and it gives you back the rank. So that allows you to start thinking about processes being in a grid. You can say, well, what process is at this grid coordinate? And also, MPI cart coords is the opposite thing. MPI cart coords says, what are the coordinates of this rank? So you give it a communicator, which has to be a Cartesian communicator. If you called MPI cart coords using MPI conworld, MPI would say doesn't make sense to ask the coordinates of a process in MPI conworld. As long as the communicator is a Cartesian communicator, you can say, what are the coordinates of this rank? So unfortunately, in the original version of MPI, until a few years ago, they only took this so far. And it turns out that when you send and receive data, you just use the normal send and receive. You have to specify a destination rank or a source rank. You can't say send a message up or receive a message down. What you have to say is, who is my neighbor up? And you just get back a rank and you send to that rank. So you're going to see, what you would end up doing is an awful lot of, you would say, what is my rank? 6, okay. What are my coordinates? 1, 2. Then for each of those coordinates, you'd add and subtract 1 to get 0, 2, 2, 2, 1, 1, and 1, 3. And for each of those, you would ask, what is the rank of the process at those positions in those times? And then you're going to have to do, which way around is it? You're going to have to do lots of cart coords and then cart rank calls, and also so what they've done is they've actually given you a much more useful routine called MPI cart shift. This says, what are my neighbors down and up, i.e. -1 and, well, down and up in a particular direction, and that's much more useful. It combines all those things. So displacement is, if you say disp equals 1, you'll get your neighbors -1 and +1. You can say disp equals 2, which gets your next to nearest neighbor. That's not nearly so common. So typically disp doesn't have to be. Direction is it the first, second, third, or fourth dimension of the grid? Okay. Now direction starts at 0, which is a bit nasty. But if you want to know who are my neighbors plus or minus 1 in the first dimension, so in this diagram here, that would be, if I'm 1, 1, I want to know who's my neighbor there and there, my neighbor down 1 in the first dimension and up 1 in the first dimension, which would give me neighbors 1 and 9. Okay, then I would call this call with the Cartesian topology. Direction would be 0, which is that first dimension. The displacement is 1, so it knows it's plus or minus 1, and this gives you the 1 negative and this 1 positive. So you have to call this for each dimension, who are my neighbors, but it's actually it's much nicer. And you would typically do this right at the start of your program. Having created the Cartesian grid, you then ask who your neighbors were and then store them away somewhere, so you have it squirreled away for later use. Okay. Now, the other nice thing about cart shift is it respects the boundary conditions. Okay. What if you ask for the rank of a non-existent process, i.e. look off the edge of a process grid? So disp, in this case here, I'm interested in my neighbors -1 and +1, -1 and +1 in each dimension, my nearest neighbor. So disp is 1. If I wanted to know who my neighbors there, up 2 and down 2, okay, then I would specify disp equals 2. It would give me what my neighbor is up 2 in each dimension and down 2, rather than up 1 and down 1. Does that make sense? Yeah, it's not so common to have disp equals 2 that you might need to know it. So what MPI does, if you use MPI cart shift, it respects the boundary conditions. So if you ask for your neighbor off the edge of a Cartesian topology, it will wrap it round. But what happens if you say, who is my neighbor there? Who is my neighbor down there? Okay, Well, there's none. So what does it do? Well, what it gives you is it gives you a special MPI process called MPI proc null. And the nice thing about that is you can send and receive to proc null. And if you send a message, it's like a black hole. It's like Unix dev null. If you send a message to proc null, it just disappears. If you receive from proc null, you just return immediately. And that means you don't need to write special code for the boundary conditions. So disp equal. So disp is a scalar. The direction specifies which dimension it is, the first, second, third dimension of the array, which is 0, 1, 2. Once you specified the dimension, you're asking who's plus or minus or plus disp in that dimension. Yeah, so there is only, so disp is a scalar. Does that make sense? Maybe I didn't explain it very well. So the nice thing about this proc null is it allows you to write generic code. You don't need to keep saying, if I'm on the edge of the grid, the next two neighbors in each direction. Well, you'd have to call it twice. You call it once with disp equals 1 and then another time with disp equals 2. Maybe that's okay, fine. Yeah, you'd have to do 2 calls. You'd have to do 2 calls. So I understand your question there. Yeah. So yes, you're exactly right. But it would be 2 calls. It's not an array. And so you don't have, with this cart shift and this proc null, it means you don't have to write special code at the boundaries. You can just say, send a message to my 2 neighbors, and if it's off the edge of the grid, it just disappears. You don't have to do lots of special case, and that's actually quite nice. That's quite nice. It makes your coding simpler. So the other nice thing you can do is once you've got we've never actually talked so far about how you create subcommunicators. And the most general subcommunicator creation routine is MPI com split, which allows you to, for each process, say which communicator it goes into, kind of verbatim. But once you've got a Cartesian topology, it makes sense to say, well, I want to split the processes up into slices. Okay, so a new communicator is produced for each slice. MPI cart sub will produce a new communicator for each slice. And that can be very nice. So for example, imagine I wanted to know the total number of cars in each lane, okay? If I want to know the total number of cars in the entire simulation, I do an MPI on reduce across all the processes, and they each specify the number of cars they have, and I get the total number of cars. But how do you think I do, if I imagine that this is the process grid now, imagine I want to know the number of cars in each lane, okay? So this lane is owned by a whole bunch of processes, but not all of them. I want to know the number of cars in that lane, that lane, that lane, and that lane separately. But I want to do it using a reduction operation. How do you think I can do it? Does anyone have any ideas? Yeah, slice by lane and then do what? So I slice by lane and I get a new communicator. I'm sure you got, but what do I do with that communicator? How do I then utilize it? Yes, you do a global reduction, as you both, you basically do a global reduction with that communicator. So when I say global reduction, they're global reduction across the communicator. So what I would do is and this is why you can see that slicing communicators is actually quite nice. You say, right, I want a separate communicator for each lane. Okay, that's actually quite a useful thing to do. So you would slice the communicator in that dimension. So you have 4 communicators. Each of those, all the processes in that communicator get together and call an all reduce. But if you pass the communicator as the slice communicator, it is collective across all the processes in that communicator, which is all the processes in that lane. And so that's actually a nice thing to do. So actually slicing communicators up by dimension is actually a natural thing to do. It's often very useful. And so MPI cart sub is a useful routine. As a slightly strange prototype, you basically, sorry, I've lost my play. MPI cart sub, you specify the initial communicator, you get back a new communicator, so each process, all the processes in the same subcommunicator will get back the same communicator. But you say which dimensions remain. So if you, so you know, because if you think about a three-dimensional grid, you could slice it up into planes or pencils. So you could eliminate, you could retain 2 dimensions or retain. So you have to say, so in this example, you would retain, the way I've drawn it here, this dimension here, which you might call the second dimension, this one here. So it's a slightly, but I mean, you can see the concept. You know, it makes sense to be able to do this, and that is actually very, very useful. Can be useful in real programs. So partition MPI. So the exercise 7 is actually rewrite the exercise passing numbers around the ring using a one-dimensional topology. So yeah, so it's an array of booleans in 4 channel or integers in C zeros and 1s. So for each dimension you say 0 or 1. So 0 means don't retain it, and 1 it means retain it. I believe that's just off the top of my head. We should check that. Yes, so if I just, that's a good question. I will share. So if you see here, this I've just done man MPI cart sub on NextGen IO, and remain dims. The ith entry of remain dim specifies whether the ith dimension is kept in the subgrid to true or is dropped false. I think to draw free data, but that you're right. That's exactly what it is. It's a little array of 1s and 0s or 4 trues and falses to say, do I retain that dimension? I think if you say retain none of the dimensions, you'll get yourself back. I think that's the extreme thing. If you would actually end up with your, I think it would be legal to do that. Anyway, that's a bit of a corner case. The exercise is, as I said, the exercise is slightly it's actually slightly out of order here. No, it isn't. Sorry, Cartesian topology isn't. It's slightly involved because it is a lot, but it says here it's worth learning to utilize these. And the nice thing you can do here is actually, once you've written your code, initially you'll use periodic boundary conditions because, of course, you want the neighbors, when you look off the end, to be. So all you're doing here is taking, if you won't have got this far because you haven't had enough time, but once you've got a working message round a ring global sum problem, a global sum program using non-blocking sends and or receives, you compute your neighbors with rank plus 1% this and rank minus 1% that. You can redo that and compute your neighbors using the Cartesian topology. It's a bit of work because plus 1 minus 1 is easier. Having done that, though, you can change the boundary conditions. So you can simply change one line of code to say that the dimension, the boundary is periodic or non-periodic, and rerun, and you actually get a scan. Because if you think about it, if you do message round a ring, okay, but you don't close the ring, so that 0 goes to 1, 1 goes to 2, 2 goes to 3, but the message doesn't come back, okay, it's non-periodic, you get a scan because the messages stop somewhere. So actually, by one change of one parameter saying this dimension is periodic or non-periodic, you will convert your own message around a ring problem from doing an all reduced to doing a scan, which is just interesting. And so, I mean, it only really makes sense to use Cartesian topologies in multiple dimensions, but I didn't want to introduce a whole extra exercise just to illustrate that. So that was really the as I said, I don't expect that you'll have completed the message around a ring yet, but that's Cartesian topologies, and they tend to come into their own in real programs, where in real programs, a lot of cases you have large, you have processes arranged in this case a regular grid, and so it makes sense to think about them being in a topology. So are there any questions about that? So I did update the instructions on the crib sheet. So if you are on NextGen.io, and I stuck up the Slurm script there, but I've also updated the crib sheet. I think I posted it in the chat window. Has anyone been able to use the Slurm yet? I don't know if anyone's had a chance to have a go and check that my script works. I think it should work, but did anyone get what we have now is the interesting thing about running upon multiple nodes is, for example, if you put timing into your message round a ring program, you will see, or well, even any program where you have a significant amount of message passing, you will see a dramatic change in timing when you run between one node and two nodes. Because of course on one node you're just within a single shared memory machine. It's like running on your laptop, multiple CPU cores in the same physical machine. But when you do more than one node, there is a physical network, and so you will see, dramatic increase in time when you suddenly have processes on a different node. So for example, in the message round a ring example, it would be a disaster if rank 0 was on node 0, rank 1 was on node 1, rank 2 was, if you did that, because every message would go between nodes. What you want there is you want ranks 0 to 47 to be on node 0 and 48 to 95 to be on node 1. Now, actually, that's often the default, but you can see that the mapping of processes to physical processors, although it should have zero effect on the correctness of your program, can have a dramatic effect on its performance. And so it's nice to be able to run on multiple nodes to see that. So there's a practical now until 3:30. Someone from EPCC will be around. Please ask questions. I would like to try and do a bit of screen sharing, even as a test, to be honest. That would be something which would be nice to do. Secondly, so I'll put up a holding slide, but we've got a practical to 3:30, then we've got a break from 3:30 to 4, and then at 4 I'll talk about derived data types, which will be the last lecture of this first block of the course. And there was an extra exercise, again, extending the message random. So keep the message randoming example isn't trivial to do at all. So just don't worry, don't jump ahead, just carry on from where you were and get a working program, because the other exercises, the Cartesian topology one and the derived data types, just build on it, but it's better to go through. So someone's just asked, do I have to call MPI com split for MPI? No. So MPI, there are several ways of dividing up communicators, and MPI com split is the most general way, but MPI cart sub is a specific way of doing it for Cartesian communicators. So there are alternatives, but the natural thing to do, so they're alternatives. You can split up a communicator using MPI com split, but it's a very verbose thing. You say, for each process, you say which communicator it's going to go into. Whereas MPI cart sub is a nice shorthand which applies only to Cartesian communicators, where you can say I want them to be split up into slices in particular dimensions. Does that make sense? Yeah. So I don't cover MPI com split, maybe I should, but if you look it up, you just basically, in MPI com split, every process gives a number. And if all the processes give the same number, end up in the same communicator. Yeah. So you could do an MPI cart sub. MPI com split is the most general way of doing it, but it's much more convenient to use MPI cart sub when you have a Cartesian topology, because that's much more short-handed thing.